I think the title of this lecture on the website, it said like something like UBM subspace stuff for speech recognition. So that stuff is going to be in the afternoon. But there still should be some things that are of interest here to the non-students, because let me go to the next slide. So what I'm going to be doing in this lecture is introducing some of the more important optimizations we use in speech recognition. Things like mixture of Gaussians, maximum likelihood linear regression for adaptation, the constrained version of that, speaker adaptive training, map training, semi-tight covariance. Obviously these things won't mean much to most of the undergraduates. I'm saying this for the benefit of the more senior people. So the way I'm going to organize this is I'm going to show you the math of it side by side with some little samples of C++ code, because since I imagine there's a bunch of computer science people here who may not be very familiar with the mathematical notation that people use, it may just help to make it a little bit more concrete if we have the C++ code. And so I decided to wake people up and to make it a little bit more interesting. There's the kind of mini game in here. Just find the mistakes. Now each code segment, at least, well, the first few ones I made sure that they have mistakes in it. The rest are long enough that there's just statistically there will be mistakes. So I'm going to be offering prizes for the people who can spot the mistakes, and you're going to have to kind of shout out or raise your hand or something if you do it. So my original plan was to give out 5s, but then I realized that it was too late to actually get enough 5s because they don't give them out at the ATMs. So in the spirit of statistics, I've decided to instead give out a prize that has an expected value of $5, which is that you have to choose a suit, like hearts, diamonds, etc. And my assistant Pinar will pick a random card, and if it's the same, then you get a 20, and if it's not, then you get nothing. Actually, this prize has an expected value of just a little bit more than $5 if you're strategic about which card you pick, because I don't think we're going to be shuffling the pack in between. But that's a very small effect. If I decide it's a particularly significant error that I wasn't aware of, then the prize is you get double the prize, nominally double. So instead of getting one chance, you get 2 chances to pick which card it is. And if it's not, if it's not right on the first try, Pinar will tell you, and then you get to pick again. So I've written, I was thinking at one point that the expected value is a little bit less than $10. Do you guys think this is right, just to get you started? Can anyone think?
That's 760.
Well, but it's the same card. Sorry?
They're not independent.
Yeah, so can I yeah, you get 2 chances to pick the same card. I don't think anyone deserves $5 for that. Okay. This was just to get you started. The other errors will be very clear. So, but you have to shout out, okay? You have to raise your hand and say the error is in here. Unfortunately, this is a little bit unfair to those who don't know C++, because most of the errors are in C++ syntax. Some of them may be more significant. They may be in the math, like in the slides. There may be kind of conceptual errors in the code. Okay, so just to get started with the concept of data, you probably know this already, but by data we generally mean some collection of mathematical objects that we want to assign a probability to. So a simple example is a sequence of discrete values x1 to xn with the x values in the set S, where S is a discrete set. So So for instance, we could have 512 values, n is 500, and then S could have size 1000. And then this code is just initializing these 512 values to random things. This is just to make it concrete. There's really nothing going on here. Does anyone see the mistake in this code? Okay. Okay, the middle guy.
There's no semicolon in the second one.
Okay, sorry to the other ones. I'm trying to make it random, but okay. So what's your pick? Which suit?
Diamond.
Diamonds. Okay, Pina.
I'm just thinking out random.
Yeah.
Yeah.
Whoa! Oh, it's your lucky day. Okay, so you have to take in the 20. Sorry? In C it returns an integer. Yeah. It's frand is a floating point. Okay. You could have got 20 there, but if you had been right. Okay. So an example of modeling discrete data. One very simple way to model these discrete values, say integers between 1 and 1,000, is we just for each value we just have like a floating point. We have a probability for each value. So and they have to sum up to 1 so that they're kind of a valid distribution. So a simple way of modeling the sequence x1 to x. We're using this curly x here to mean the sequence. It's common notation to use that kind of thing. So that means the entire sequence. So the probability of the sequence is, just the product from 1 to n of the C of C sub x sub n is like, x sub n will evaluate to a member of the set S, like an integer between 1 and 1,000, say. So this would, evaluate to C sub, that C sub 200 or whatever. So the probability of the sequence is just, So it's the independence assumption which says that you can just multiply up. If you're modeling the joint probabilities, it would be more complicated. So and we call these the parameters. This C sub S, these values are parameters. Like before, they should sum. Like I said, they should sum to 1. So this is just an example of setting the C sub S to to be all the same. Again, this is just to make it concrete. Okay. You.
You're missing the S plus plus.
Good. Okay. So.
Hearts.
Sorry.
It's not your lucky day. Okay. I'm not going to let other people pick, if multiple people have their hands up, because then it's inevitable that someone's going to get the 20 each time, so I'm going to be out. Okay. This is an example of evaluating the probability of the data given the model. Just, again, this is something pretty obvious, but just to make it concrete. We want to compute the probability P of the sequence X, which is, as I said before, this product. And typically in real situations, you compute this as a log value because this value could get either very small or very large, in this case very small. And the floating point range won't be able to handle it. So we just compute log px as the sum from 1 to n of the log value of that. And what we typically do with these log probabilities is we might be comparing them between different models. Say it's a classification task. So we might be seeing which one is higher, stuff like that. But I'm not going to go into the details of that. So this is just an example of computing the log likelihood. This, we're just checking that all our integers are valid so we don't get a segmentation fault if someone gave you the wrong data. Now, I'm trying to remember what the mistake was in here. There must be a mistake. Can anyone see a mistake?
Right here.
What?
You go 0 to n instead of 0 to n minus 1, or 1 to n.
Wait. This one?
Yeah.
0 to n.
Excuse me.
Oh. Wait.
Good. It's good.
Okay. I'm sure there was a mistake. I think I made sure there was a mistake.
There's another, like,
Go on.
you can't do float as comma int and.
Oh, yeah. Wait. Float. Oh, yeah. I put that one in intentionally, by the way. My hands would never. Okay. So what's your pick? Clubs. I'm sorry. Uh-huh.
What if C is equal to 0? I mean, log cannot be computed if C of x is 0.
Well, I suppose that's true, but you could have made.
I don't want your money. I'm just.
That is true. That is true. Yeah. Do you think that deserves a try? I'm going to let the audience decide in ambiguous cases. Do we think that people are saying no? I'm sorry. Okay. So again, I just want to introduce the concept of statistics of the data. So in order to train this model, this C sub s values, we want to the way we typically do this is we want to maximize the probability of the training data given the model. I just noticed this, but I don't think this is the kind of mistake I meant. And this is equivalent to maximizing the log probability, that we computed before. It's equivalent because log is a monotonic function of, of its argument. So if you maximize one, you maximize the other. This is equivalent to the sum of these values ns times log c of s, where ns is the count of the value s in the data. So ns is just the number of times that value occurred. This is kind of obvious just from rearranging this, to group the n's together. So these count values, we call them the statistics. And in general, statistics are not just counts, but they may be like things like means or like sum of squared of the data. Often the counts aren't like whole numbers. They would be between 0 and 1 and things like that. This is just to get you comfortable with the concept of statistics. And if the statistics are sufficient that you could kind of work out P of x from the statistics alone, then they're called sufficient statistics. I think I looked up the real definition of sufficient statistics and it was very technical, but this is the general idea. So here is just an example of computing the count. And I think, what is it?
Big S instead of.
Yes. Okay, so what's your suit?
Spade.
Spades. Oh, you're the first one to pick spades. Let's see if you're lucky.
No.
Uh-oh. A lot of people are having bad luck. Okay.
Actually, you would change the first need we have in this
Yeah.
expression. Because if you say we call them sufficient statistics, because once we add them, we have all we need.
You're right. Is that an error? Yes, okay. So what's your suit?
I don't know, hearts maybe?
Now it has an expected value of 0 because we already saw what it was. Okay. By the way, are people being strategic about which suit to pick?
You have to
No?
count, right?
Sorry?
You have to count.
Yeah, you have to count, yeah. Okay. So here is so after you get your statistics, here is an example of how you compute your parameters. So we want to maximize this given the ns. Now the normal derivation relies on Lagrange multipliers, and I always forget how to use Lagrange multipliers. It's very easy to mess up. So I derived a simpler derivation. The derivation is, imagine quantities c hat sub s that don't necessarily sum to 1, but which don't sum to 0. So this is kind of a renormalization. Cs is c hat sub s divided by the sum. So that kind of renormalizes them to sum to 1. And then we optimize the c hat sub s. So this value, the value in the brackets here, is equivalent to log of c sub s. and this is just, you know, substituting the expression for C sub s in terms of C hat sub s and rearranging it a little bit. So now we're computing the gradient of P of x with respect to one of the C hat sub s's. And it comes out to, let me see, ns over C hat sub s. This comes from this expression, minus the sum over all of them. Let's see, what's this top one? I think this is like the total count. Is that the total count? No, yeah, this is the total count, and this is the sum of the C hat sub s. So I'm just defining t as the sum of the C hat sub s. This is the value that, like I was saying, may or may not be equal to 1, but shouldn't be 0. And if we set this gradient to 0, you know, because that's always what you do when you're finding the optimum of something, or the maximum or the minimum, and defining t as the sum, you can kind of rearrange 0 equals that, rearrange a little bit, and you can get C hat sub s equals t times this ratio. And then if we set c to 1 to make the C hat sub s equivalent to the C sub s, because they sum to 1, the answer comes out. So the answer is that C sub s equals, you know, the count divided by the total count, which is kind of what you'd expect. So if you saw 1,000 samples and you saw something twice, then your probability is 2 over 1,000. So here is just the kind of update code given the previous statistics that you, what is it?
You should float the count first instead of float the result.
Yeah, right, yeah. I inserted this error on purpose. Yes. Because if you do this, then it kind of rounds it to an integer, and the answer is always going to be 0, because both of those integer values.
Are we supposed to do this at the end?
Do what?
After you stop tracking, we should do this, because otherwise people would be jumping all over the place. No. I want to do it like this, because the thing is, otherwise it just becomes a question of who can raise their hand first. Because then a bunch of people will see the error, and then by the time I get to it, you know what I mean? So I prefer to do it like this. I like chaos. So what's your suit?
Still spades.
Spades. Okay, is that your lucky suit today? People are having bad luck today. I've only given out 120, and I've had like 6 or 7 different. Do you think we should start giving people 2 tries? No one's saying yes. Okay. So this is, I'm not going to describe what HMMs are, because the previous lecturer should have done that, and it kind of gets complicated. But I just wanted to mention that the kind of discrete probability model that we've been talking about, this used to be the state of the art in speech recognition. What people used to do is you have this continuous speech feature based on Kepler's coefficients. And people used to kind of vector quantize it to, let's say, 256 VQ bins. So you kind of get a discrete value. And then in each HMM state, you would have this discrete model with, you know, the C sub s. And, you know, for many years, this was how they did speech recognition. And then at some point, people moved over to using continuous models with Gaussians and stuff like that. So I just wanted to mention what the difference is between the estimation I just described and what you do in HMMs. And you probably should have done some of this. But the difference is that instead of the n sub s being kind of integer values, they become kind of summations of continuous quantities. These gamma j of t, these are kind of values between 0 and 1, which describe the probability of being in a particular state on a particular time. So you can kind of think of them as soft counts. So basically when you do the estimation, instead of computing the sum over real counts, you compute the sum over soft counts. And there's this forward-backward algorithm to compute what the soft counts are. And I'm not going to go into all of that stuff because that's not really what this lecture is about.
Summation at the bottom, what is this R? Sum R equals 1 to 3.
Oh, you're right. That should be big R. Oh, that's a mistake, isn't it? What's your card?
No, my question is, what is this R? Is this
I didn't introduce it. Well, let me see.
utterances or-
Well, I guess I must have been utterances, yeah. I mean, in Cambridge, that's the way they do it. I probably shouldn't have had this R in there at all. I guess it's just out of habit that I typed it. But I think that definitely deserves a pick. What's your suit?
Let's move on. We will tell him the end now.
He's embarrassed to go on.
The commas need to be subscripted or it should be a function of S also, right? The way you written.
Oh, you're right. Yeah, you're right. I think. Oh, wait a minute. No, I think. Yeah, the S should be there somewhere, shouldn't it?
Yeah.
Well, J is the state, and I think S is like the discrete label. So I suppose we should probably have a delta function here that says, at some point was the observational time t equal to S. So I think it's maybe not a question of having a subscript somewhere, but to have, for those who don't know, delta, if delta brackets I comma j, let's say, is a function that's 1 if I and j are the same and 0 otherwise. So probably you'd have, delta S comma like S of t, where S of t is the discrete label on time, or maybe X of t. Maybe that would be a better label for it. Normally because we don't really do discrete HMMs, we don't see expressions like that, but that's probably how you would write it. So I just wanted to introduce the concept of a likelihood. The likelihood is a term that we often throw about without really thinking about what it means. So now, okay, a probability density function. It's a function of a continuous variable which says how likely the variable is to fall within a particular region. So, for instance, for a scalar x, like say a floating point value, it should satisfy, or a real value in mathematical notation. P of x must always be more than 0, otherwise, a probability can't be negative, more than or equal to 0. And it should integrate to 1 from minus infinity to infinity. This is just so that, it can be a real probability. But by the way, I just wanted to put this line is just meaning that this probably isn't really right. In a mathematical paper, instead of saying a PDF P of x, they would probably say a PDF P colon R, arrow R. It's just this is like a declaration. Mathematicians kind of write stuff like this, that a function P that takes a real value and gives you back a real value. Yeah, that's that. So the meaning a PDF has is that the probability of x being in a range from a to b equals the integral from a to b of the P of x. So, like let's say the P of x is that. To find the probability that x is between here and here, we compute this area. So, I just wanted to make clear what this notation means, because if you're not mathematicians, it may not be clear. I believe with parentheses, it's a range x strictly between a and b, and with brackets. In computer scientists would call them brackets. I guess other people would call them square brackets. It's a closed range, less than or equal to. Mathematicians make a big deal about these distinctions for almost all situations where someone like me would be concerned. It really doesn't make any difference at all. I just wanted to mention what a likelihood is. We often talk about likelihoods. A likelihood is what a PDF returns. So if you evaluate this PDF, P of x, at a specific place, you get some value, and that value is called a likelihood. And likelihoods are they're analogous to probabilities, but they're not probabilities. They're like, if you're dealing with continuous variables, you have likelihoods, but they're not probabilities, and they're not even necessarily less than 1, so it's clear that they're not real probabilities. They only really have meaning as probabilities if you talk about these integrals of them. So something that a lot of speech people forget is that you always have to use the lowercase p for likelihoods and the big one for probabilities. I just wanted to mention what a CDF is, a cumulative distribution function. It's like the integral from minus infinity of a PDF, for instance. Integral from here, minus infinity to x of p of x. So, and it's equivalent to the probability that x is less than k. Of course, CDFs are only applicable in the scalar case. If you have vector valued quantities, there's really no analog to integrating from minus infinity, so it's mean. And we often don't deal with these, but CDFs are a little bit more general because if you have a value that has little spikes, so let's suppose we plotted the value of this game that we're playing with the $20, but basically it would have the function would have a spike at 0, and it would have a spike at 20 of about one third the magnitude, and these are kind of Dirac delta functions, and they're not like proper functions. That they're distributions, but they're not really functions. So the PDF, in a sense, doesn't exist. But the CDF does exist because the CDF is like something like... No. Yeah, I think the CDF is something like that. So the point is that there's situations where the CDF exists, but this PDF doesn't exist as a proper function. So this is why they're useful. But for the cases, go on.
So why do you say they don't exist in the vector case? I'm sure that's...
Well, what does it mean to integrate from minus infinity for a vector case? Would you like integrate all dimensions?
Just integrating up to a point, right?
I mean, there is a definition which is...
There is?
Element-wise, you say...
You integrate element-wise. But what does it mean? I guess it means that they're all less than that.
They are all less than...
I suppose. I think it's just not a very useful definition. Go on.
So, in this minus infinity to x, you won't take the whole area. It's discrete points. So
Well, no. The whole point of...
points. If
No.
there is a direct delta function, it's just discrete points. So
Yeah.
you will sum up the discrete points, not take the integral.
Well, no, but the whole point of this is that this is a continuous value. This was just a kind of this was just an example of what it looks like if they're discrete. But these would not normally be discrete functions. They would be continuous ones like that. Maybe I misunderstood your point. By the way, do you think this observation about the CDF existing deserves a chance?
Well, mathematics is built on it, right?
Okay, I think Fred thinks so, and Fred's voice definitely counts. So pick a card. Clubs. You guys are not having good luck today. Go on.
You should be integrating over p of y after the fact.
Oh, I think that's a genuine mistake. That's a quite. Do you think that deserves two toothpicks? I think that's in the math. I'm not going to just pull out a 20, but I think that's an error that I wasn't aware of, and that's an error in the math. So I think that actually deserves 2 tries. So pick it. So you're not. So don't. By the way, the first try, don't tell him what the card was, because then it's obvious. Okay. So what's your first pick?
So wait, what is the game again?
The game is you get 2 tries to pick. If you're wrong the first time, she'll tell you that you're wrong, and you get to choose again.
Okay, diamonds.
It's okay if I see it.
No, it's wrong.
It's wrong.
Diamonds.
What?
It's the same card.
Oh, it's the same card?
Yeah.
Hearts. It's the same card.
Yeah. It's the same.
Same card. Okay.
Right. What was it?
And you have to look at the card and pick
It was clubs. Okay. Okay, I just wanted to go over values in the vector case. What this slide is about is mainly issues of notation, which they may seem a little trivial, but it's good to get comfortable with the notation. So, for vector value features, x in Rn just means x is an n-dimensional vector. I just wanted to. I don't know if I should even mention this. Just wanted to explain what this notation means. This is obviously set theoretic notation. X is a member of. So R is the set of all real numbers. Rn is a shorthand for R times R times R,
which is the Cartesian product of the set R n times. And Cartesian product means it basically means taking the pair. So it's like, so R times R would be a pair of, two reals, and then R times R is like a kind of tuple, which means just like, 4 of them or 5 of them or whatever. So now the constraint on probability is now this, the integral over the whole R to the n, p of x times d to the nx equals 1. The reason there's an n above here, I never used to be very rigorous about this. I probably used to usually write dx. But it turns out you really should have d to the nx because, and this is Riemann's integral notation, which is most of the time if you're doing integrals, that's what you're using. D to the nx is the volume of a small region. You can think of it if the, the integrals are defined in terms of the limit of like little rectangles or whatever. This is how people usually define integrals, and it's the limit when these little regions become small. So in the volume case, I suppose what you'd be doing is you'd assume these little intervals correspond to little cubes or whatever, and so d to the nx is like, it's like the product of the sides of the cube, so it's the kind of volume of the cube. There's another way that they define integrals called the Lebesgue integrals. It's spelled Lebesgu. It's some French name, and this is the kind of more advanced kind of integrals that mathematicians use. But it's defined in terms of all sorts of very complicated stuff called measure theory and stuff. You really don't want to get into that. But the reason they're useful is that there's certain kinds of functions that you can integrate with that you wouldn't be able to integrate with a Riemann integral. Like you can't really use Riemann integrals for things like Fourier transforms because it doesn't converge properly. Anyway, so I just wanted to be clear about the notation. So just on the distinction between d to the nx and dx, dx is what you use if you're doing a line integral. So let's say the integral along a line from here to here. And then in that case, dx is just the vector, the vector valued length of this little segment. So if we had dx instead of d to the nx, then dx is that kind of corresponds to a little vector value, a kind of infinitely small vector. Anyway, so like I say, the interpretation of the likelihoods for the vector case is that p of x in w, where w is like a small volume or a region, is the same as the integral over the region of p to the p of x. And again, you should interpret these integrals as like the sum of the volumes of little cubes.
Is it type on there?
Where?
When the x should be bold on the line before the last. P of x there should have been bold.
Oh, you're right. Does this deserve something?
No, I'm not saying.
People are saying no. I'm not going to decide. I'm going to let the audience decide. That's my plan. Okay. The most common continuous distribution that we use in things like speech is the Gaussian distribution, sometimes called the normal distribution. Although I don't know if when you use the word normal, it implies that kind of the variance is 1 and the mean is 0. Is that right? No. It doesn't. Okay. So it's the same thing. That's how I use the letter n, by the way. It's normal. And this is equal to exponential of -1/2 times log 2 pi plus log of the variance plus x minus mean squared over sigma squared. The Gaussian distribution is the bell curve. It looks just like this. And this isn't the scalar case. Now in the vector case, it's written like this. Now there's a mistake in this expression. Yeah, it should be transposed. Okay, so do you want to pick? There was someone behind you too, an undergraduate. Let's let the undergraduate go. You're not? Oh, I'm sorry. I didn't recognize you. Okay, so Arnaud then.
Spades. Oh! Oh, it looks like maybe the graduates are having better luck. Okay, Pina will take it. Oh, okay. So just to make this again a little bit concrete, I've written down some code. I don't know if there's actually any errors in this code. If you can find some, then you get to pick a suit. But this is just computing. Okay. Now it's common to make these sigma values be diagonal matrices. These are matrix valued things. But it simplifies the calculations a lot if you make them diagonal. And also, if you have a limited number of data points to train them, it kind of increases the accuracy of your estimates. So it's common to make these diagonal. And in that case, it will just be like the same as an array because you're storing the diagonal elements. So this is how you would compute this function for a diagonal one. And this is how you compute it for a full one. In the full case, because it's sigma inverse that appears here, you would normally store the variance matrix as an inverse matrix because otherwise you have to invert it each time. So I'm kind of assuming that it's stored that way. And you have to compute the log determinant. I assume everyone has at least some vague idea of what a determinant is. I guess I'm not really going to get into that. Okay, so I guess there's no mistakes in there. My assumption was that in code as long as this, there's bound to be an error, but I guess we'll know when we compile it. Okay, so training Gaussian distributions. By the way, can someone tell me what the time is so I know whether I should go faster? 20 to 10, okay. There's a lot more to go. We're probably not going to finish this, but let's just see what the natural speed is. So supposing you're training one Gaussian distribution on a collection of points x1 to xn, where these x's are vectors. So the sufficient statistics, we call them the zeroth, first, and second order statistics. The zeroth order statistics are just the count. It's just the count of the data. And if there's just one Gaussian, it's just going to be one value, so there's no subscript. It's just n. The first order, this is not really standard notation to use the letter m. I'm just using that because it's convenient. The first order statistics is the sum of the data. The second order is, that's wrong. Okay, I guess I noticed that, so should I pick a, there's not much point. There should be xn transpose. This is the outer product. So let me just write this down in case you guys are not familiar with it. If x is a column vector, let's say it's 1, 3, 4. X transpose would be a row vector, 1, 3, 4. So x transpose, it's kind of like a backwards product because when you multiply matrices, you multiply a row by a column. These are backwards, so we multiply this row, which of length 1, by this column of length 1. So we end up with something like, 1, let me see, this row goes 1, 3, 4, 3, 9, 12, blah, blah, blah. So this is what the outer product is. The point is that S is a matrix. And notice, of course, that we use bold lowercase for vectors and bold uppercase for matrices. Go on.
If S is a matrix, it probably should have 2 stars before it in the operation.
Before what?
Where it says float star.
Oh, yeah, I think I put that one in on purpose. Okay, so what's your suit?
Space.
I guess we're learning the meaning of expected value today. Okay, so I just wanted to. This should perhaps be useful to some of the people who've been around a bit. I've come up with a kind of simplified explanation of vector matrix calculus, which is useful in speech situations. So in kind of speech situations, you normally only need to differentiate a scalar valued function with respect to vector or matrix valued quantities. So for instance, a likelihood is a scalar value because it's just like a float. It's a real number. It's not a vector. So
But you often need to differentiate these with respect to vector valued or matrix valued quantities. So for instance, you might need to compute d by dx of x transpose ax, and this is a scalar because it's like an inner product, you know. X transpose is a row and ax is a column, so it's just like it's a single scalar. Now, okay. Now the gradient of a scalar with respect to a column vector is going to be a row vector. There's a kind of transpose. Now this is only one convention. Some people use the opposite. But the one that I'm favoring in these slides is a convention where the gradient, the differential of a scalar with respect to a vector is always going to be transposed. So, you can define the gradient very easily in terms of the elements of the thing. So, let's see. If V transpose equals df dx, the reason I use this notation is that normally if you write V, that's going to be a column vector. So, since df dx I'm saying is a row vector, I'm writing V transpose equals that. So some people actually write down letters like V and explain that they're row vectors, but I think that's not normal. Perhaps someone could correct me on this whole issue if this is a reasonable notation, but this is what I'm saying. So if V transpose equals df dx, then the first element of V equals the gradient of f with respect to the first element of x. And notice that I'm using these curly deltas because it's a partial derivative. When you have multiple variables involved in some kind of equation, if you're just computing the gradient of the thing with respect to one or leaving the others fixed, you should use these curly letters. Now in vector matrix calculus, the result that you get, it's generally kind of equivalent to what you would get if you just considered those quantities as scalars. So for instance, d by dx of x transpose ax, the answer is going to be x transpose times a plus a transpose. And in the scalar case, d by dx of x squared a, it's just going to be 2ax. So you can kind of see that the x is here, and then this kind of corresponds to 2a. Go on.
There's the last expression.
Yeah.
It should be x transpose ax and a is a symmetric matrix.
Sorry?
It should be x transpose ax and a is a symmetric matrix. The last expression. Yeah.
These are scalars. Wait, this expression?
Yeah.
No. What I mean is that these are scalars. You probably can't see that, but this is a non-bold font, right? So what I mean is that these are scalar values. So they're not matrices, right? Okay. Okay, so this slide was just about the issue of whether or not it should be transposed, and this is getting a little bit. You have a comment? Okay, this is just getting a little bit obscure, but some people don't actually transpose the derivative. If someone's writing down equations with this stuff in, it should usually be obvious which convention they're using. But the rationale for the convention we use here is that df dx, this is a concept from physics. It's like a covector to x in the sense that a multiplication of the two would kind of make sense dimensionally. Physicists, it relates to all this notion of like coordinates and whether, if you change the coordinates that you're working in, whether or not things will still make sense. Covectors are things that, if you kind of change the coordinates, the product between a covector and a vector is always going to stay the same. But so I'm not going to explain this very exactly. This is just an example. I'm not going to go into this. Anyway, either convention is okay as long as you use it consistently. I'm not going to go into this. I mentioned this before. So something that's very useful in vector and matrix calculus is the trace operator. Trace is a very trivial function. The trace of a square matrix is the sum of its diagonal elements. So suppose your matrix is, like 1, 2, 3, 4, 5, 6, 7, 8, 9. So the trace of this is 1 plus 5 plus 9. It seems like it wouldn't be very useful, but it is quite useful in these kinds of situations. So, and obviously for a scalar value, a scalar is just kind of equivalent to a matrix with
with one element in it. So the trace is just X itself. Now the trace of a matrix A times B, if you actually work out what A times B is in terms of the elements of A and B, you can work out that it's equal to the sum of indices I and J of Aij times Bji. So it's basically each value in A times the corresponding transposed value in B. So like if A is like this and B is like this, it has to be like this because the answer is going to be square. So A and B are going to be flipped. So it would be like the sum of all values of some value in A times the corresponding transposed value in B and sum of all values. So, and this implies that, let me see, the trace of A times B transpose is sum of Ij of Aij Bij. So if you take the transpose into account, the trace operator of A and B, it's kind of like a matrix form of dot product.
You are assuming here that the matrices commute with each other. They are square matrices.
Well, no, they're not necessarily square, but they.
So then why don't you put a transpose like
Where?
CD?
Well, the trace of.
C transpose, right?
Wait, where?
When you reverse the
Yeah.
multiplication, you have to transpose the matrices, right?
Oh, you're talking about here.
Okay, well.
No. This is special. This is about trace. This is actually true. This is not true because AB equals BA.
Right.
This is true.
You are just taking the trace.
Yeah.
Can you just say real quick what's the trace of a rectangular?
Well, it's undefined. In
The size is different, but
it's undefined. If you actually evaluate it in something like MATLAB, it will give you an answer. But from a mathematical point of view, it's not defined. So, okay. Now it's possible to.
The dimensions don't agree. You may not be able to pre-multiply.
Yeah. So the dimensions have to. Okay, it's possible to show that trace of AB equals trace of BA. I think this probably follows from. Let me think. I think it follows from some of these previous facts, but it's not hard to show.
The fourth equation is the
so
diagonal
if
elements
there is
are
a
always
3
the
by
same.
4 matrix multiplying a 4 by 5 matrix.
3 by 4 by 4 by 5.
Right.
Well, the answer wouldn't be square, would it? The answer would be a 3 by 5 matrix. Therefore, trace would be undefined. So I guess these are only valid when trace itself is defined. Okay. Yeah.
Hence AB and all.
Okay. So trace of AB equals trace of BA. This implies this implies that you can take any expression at the beginning of a trace equation and move it to the end and vice versa. Because, like in this equation, if we just bracket B, C, D and kind of make it equivalent to B here, then we can just move A to the end. And don't forget that these are all true. I've written A and B like they're matrices, but they could be vectors too. Vectors are like, matrices with one column or one row, so it's perfectly valid in that case. Trace of A equals trace of A transpose. This is obvious. It's just the diagonal, and that stays the same. Trace of A plus B is trace of A plus trace of B. This is obvious too, because everything's linear. Go on.
For people who are not familiar, it might make sense to make the distinction that trace is not generally commutative, that you can only do the cyclic transformation. So if it's ABC,
Yeah.
you cannot say
ACB. Yeah.
Right.
Yeah, that's true. Okay, so I've kind of come up with a rather partial. I've kind of come up with 3 rules that allow you to do vector matrix calculus relatively easily. Normally you have to learn about 10 or 20 different rules, but I can kind of come up with a formulation that allows you to do it rather simply. This isn't very properly formalized. Some of these definitions are not very formal, but they allow you to do what you need to do. So it's easy to show that d by dA of trace of AB equals B. Now this is because, recall that if we write something down like trace of A, B transpose, this kind of corresponds to the dot product in the sense that you take each element of A and multiply by the corresponding element in B. Now, remember that there's this whole transpose thing going on in this particular formulation of matrix derivatives. So, well, basically what's happening is that this transpose is cancelling with that transpose. And this whole thing is a little bit like a vector dot product. Because think about if you have x dot y, where x and y are vectors, it's obvious that d by dx of x dot y is going to be kind of equal to y, or maybe y transpose. Because, you know, this is just equal to the sum of over the indices of, you know, xi, yi, and, you know, d can be d by dx, and so like d by dx1 is just y1. So this is just to motivate why. You can easily work out this fact, but this is just to, you should probably think about this in terms of vectors, because this trace thing is kind of equivalent to a dot product. So now, this I haven't really properly formalized. What I mean by this kind of this approximately equal to notation, I mean that this is a linear approximation, so it's kind of locally, it's locally valid. And I should have made it much more formal, but that would be very complicated. So what I mean here is delta is like a change in A. And f is a scalar valued function of these matrix values. So this is approximately equal to f of A, or, you know, obviously this is at the current location, plus the trace of delta times df dA. Remember that df dA is kind of transposed with respect to A. So if A is this shape, then df dA is this shape. And the product is square. This again, this is very easy to show that this is a linear approximation based on, you know, all the definitions. Now, these two are kind of about the product rule. If you remember in normal calculus, you have this product rule that says d by dx of f of x, g of x is, you know, it's going to be like f dash of x. I'm using inconsistent notation. I mean, this is d by dx of f of x, but it's quicker to write dash. F dash of x, g of x, plus g of x, g dash of x, f of x. Now, okay, this is what they normally do for matrix calculus. So they normally use a conventional product rule like that. But the problem is that in the matrix case, think about if f of x and g of x are kind of matrix valued functions. Basically, you have to compute the derivative of a matrix valued function with respect to a matrix valued function. And this is a quantity that has like some enormous dimension because you know, if you have a matrix and compute the derivative with respect to another matrix, you have to think about the gradient of each element in one matrix with respect to each element in the other. So it becomes a quantity that has a dimension of like the number of rows times the number of columns of one by the number of rows times the number of columns of the other. And we start having to worry about how to multiply the rows and columns together and stuff like that. It just gets very nasty. So I'm using a kind of simpler way of doing this, which just says that each time A appears in an expression and we're differentiating with respect to A, we differentiate with respect to that A and treat everything else as a constant. Now this is my attempt to formalize this. It says that if f of A equals g of A, h of A, where g and h can be scalar or vector or matrix valued functions. So the notation here implies that they're scalar, but they don't have to be scalar. We define A bar as A. A bar is kind of like the current value of A at the point where we're differentiating, but we treat it as a constant. And then we say df dA is derivative with respect to A of g of A bar h of A plus g of A h of A bar. Oh, I should have a brackets here. This really needs to have brackets around here and here, because the differential is priced at both. And by the way, the reason I'm using curly deltas here is because we now have the A and the A bar involved. And the curly letters mean we're only differentiating with respect to the A. The A bar is separate and considered as a constant. And if, go on.
But then you need a curly in the second expression. The second
You mean here?
The curly for age. I mean, the product always involves two derivatives, one for respect to one function.
Oh, you mean I should have this here? Yeah, that's what I was saying about the brackets. I really should have brackets here.
Oh, sorry.
Yes. Okay, so here is an example of doing this. Suppose this is a very common thing that we need to differentiate in speech kind of and Gaussian computation. We want to find the derivative with respect to x of x transpose ax. This is a scalar value. Because think about it, x transpose is a row and then ax is a column, so it's... so we add the trace, because as we said before, the trace of a scalar equals just the scalar value. So you can do this, and it's going to be the same. Then we use our special product rule. Using x bar equals x. So we have d by dx of trace of x transpose a there, plus that. And now we have this rule that trace of AB equals trace of BA. So, and we have a rule that trace of A equals trace of A transpose. Basically, we can manipulate these expressions using these two rules and get them into this form. Let's just consider how to do that. So we want to get this one into... No. I'm trying to think which one corresponds to which one. I think... Let me see. We want x on the left. I forget exactly how to do this, but it's possible. So now let's go back to our previous slide. Rule 1. Rule 1 says that d by dA of AB equals B. That's very simple. So we're applying rule 1 to this stuff. And so in this case, A corresponds to x itself, and B corresponds to this bracketed expression. And then, in this one too. So that's why we get this when we apply rule 1. And then we discard the bar at this point because x and x bar are the same. It's just we introduce the new variable for differentiation. So then we get that this is the answer. So, so that's our final answer. So this is how we derive that expression. Here's a slightly more complicated example of how we can use this. And yeah. So we want to work out the derivative of the determinant function. So now it's possible to show that d by dA of det A is unity where A is the unit matrix, where A is the unit matrix. And the reason why this is possible is that the determinant is defined in terms of the cofactors. I think the cofactors are like the determinants of the... Let me see. If you have a matrix like this, the determinant is the sum over, let's say, the first row of this value plus times the determinant of the rest, plus this value times the determinant of the matrix that's this and this. There's some signs involved. I forget exactly the signs involved. But the point here is that if something is on the diagonal, the determinant of this is just going to be 1 if we're talking about the unit matrix. Because the determinant of the unit matrix is always 1, and that's easy to show. But if it's off the diagonal, let me think about this. I think it's possible to show if it's off the diagonal that the determinant of the rest is 0, because, let me see. I think the issue is that this is a whole column here that has all zeros in it. And if a matrix has all 0 in a column, it's easy to show that the determinant is 0. Because you could just take the summation over this row of these values on the determinant of these. And since these are all 0, the sum has to be 0. Anyway, so I'm just giving you some flavor of how you would show this. I haven't done the entire derivation. But now because determinants are multiplicative, so the determinant of AB equals determinant of A times determinant of B, we can introduce an A bar again. So d by dA of det A around A equals A bar. is d by dA of this times this. Now, the reason we do this is that now this is obvious because the A bar just cancels. Determinant of an inverse is just the inverse of the determinant. So, but the reason we do this is that this is now going to be approximately the unit matrix, and this is just a constant. So now let's substitute the letter B for everything inside the bracket so that we can just it just makes things simpler. So then we can use d by dB as determinant of B as unit matrix, since B is approximately the unit matrix. Obviously that's the case because these are inverses of each other, so it has to be the unit matrix. So then we use rule 2. Let's go back to what rule 2 is. Rule 2 says f of a plus, a linear approximation to f of a plus delta is f of a, obviously, plus the trace of this product. So let's go back. We're saying we use 2 to get determinant of B is, now 1 is like the determinant of the unit matrix. This is just like the constant term. And this is the delta, the difference between something and the original value. And this is the gradient. And we can, let me see. I think the way we get from here to here is use the fact that the trace of I times I is the dimension. Obviously, because we're just adding ones. We're adding d1s on the diagonal. So, let me see. So then so I think we're using this approximation to trace of B, and we're inserting it into some expression here. Determinant of A is det B, det A bar. So determinant of A is approximately det A bar times det B, and det B is this thing in the bracket. And I think it's, I think at this point everything is scalar. And to go from here to here just involves scalar manipulations. And sorry? Yeah?
I would find it useful if you define as a limit what d by dA is.
D by dA.
You know, just like we define d by dx.
Yeah, I see what you mean. Let me think about that. That's not something we can really do here. So I just wanted to use this vector matrix calculus to derive the standard formulas that people use for working out the mean and variance of a Gaussian distribution. The Gaussian distribution, remember this is small p because it's a likelihood. It's equal to some, I think this k is just like the 2 pi terms that we're not interested in because they don't really vary with anything. It's like minus 0.5 times the count, gamma is the count, times the determinant of sigma. I didn't really derive this whole expression. What this expression is, this is like the log of the product of likelihoods over the whole sequence of x. But written in terms of the sufficient statistics. Remember that gamma is the count, m is like the sum of x, and big S is the sum of the outer products of all of the x. And it's possible to do some manipulations to show that the log likelihood of the entire sequence equals this. Now, and by the way, all of these mu's should be bold, but the program that I created this thing in doesn't really do bold for Greek very well. So anyway, so we differentiate with respect, first we want to compute mu. What should mu be? We differentiate with respect to mu and set to 0. So the d by d mu of all of this equals 0. We can ignore this part because this doesn't vary with mu. So it's possible to use, the previous rules that I described to show that mu transpose plus gamma, m transpose plus gamma mu transpose times that equals 0. This just follows from differentiation. And that can, because this is just the same as like 2 sigma inverse, because sigma is symmetric, so transpose doesn't do anything. And because sigma is always going to be kind of positive definite, the only way this can be 0 is if this is 0. Anyway, it should be kind of obvious from the scalar case that if you want this to be 0 and this is not 0, then this has to be 0. Anyway, so the answer is mu is 1 over the count times m. And this is kind of obvious. This is just saying that we're computing the average of the vector-valued quantities x. And obviously that's kind of what a mean is, right? So that's why we call mu in the Gaussian distribution the mean. So the next thing is we want to compute the variance. And it's actually more equivalent to directly compute the inverse variance, because the differentiation just turns out to be easier in that case. So if we define t as the inverse variance, we differentiate instead to 0. And we get some expression like this. And you can show that the t minus 1, which is equivalent to the variance, is like, S is the scatter matrix, it's the outer products. So we just divide this by the count, subtract the outer product of the mean, and that's the answer. This is, I'm not going to go through each step because this is going to be a diversion. Okay, so the distribution that we commonly use in speech is a mixture of Gaussians. And a mixture of Gaussians is a distribution that we have, say, m different Gaussians with possibly different means and different variances. And we model a distribution with a sum. The reason we use this is that not all distributions are really Gaussian. Like, suppose you have some data that's really distributed like something like that. That's not really Gaussian, but we can approximate it with a mixture of Gaussians. So we have like one Gaussian here, and one Gaussian here, and one Gaussian here. And if you add them up, it's going to look a little bit similar to that. So, and I think people have theorems that they show that you can approximate almost any distribution with a sufficiently large number of Gaussians. So then it becomes, you have the problem, how do we maximize the likelihood of the data with respect to this mixture of Gaussians? And this is where we get into, there's this whole theory called EM, expectation maximization. And someone's made this very general theory that's very hard to understand, but I'm just going to explain it to you for this specific case, which kind of gives you the general idea. And now first I'm going to explain how the computation works, and then I'll go into the derivation, just so you have some idea where we're going. So now this assumes that we kind of have some initial estimate, maybe a random estimate, of the parameters. The parameters are the mixture weights C, the means mu, and the variances sigma. So and we have some sequence x1 to xt of training points. So for each element in the sequence, we compute the proportion of the likelihood accounted for by Gaussian m. So for each Gaussian, we compute this gamma m of t. T is like the index on x. So if we have x equals x1, x2, x2 up to xt, and like t is the index value. So on each time t, we have these gamma m values that sum to 1, and gamma m is just it's like the ratio of this for the first mixture divided by the sum. It's like how important this mixture is to this data point. So then now these are between 0 and 1, and they sum to 1, and these just become weights. You can think of them like importance weightings. Yeah, they're posteriors. So now, normally, previously this gamma was just like the number of observations. But with these weights involved, gamma for the mixture m, it becomes the sum from, I think I'm using inconsistent notation here. I changed at some point. I was using n, and then I changed to t, but they're still mixed up. So just understand that. So the gamma is the sum from
over the training data points of the individual gammas, and then this M statistic, which was previously the mean, it becomes a weighted mean, and this S, which is a scatter or outer product, becomes a weighted outer product. And the update equations are just as before, using these statistics. It's just you have the extra index on it. It says like which mixture are we thinking about. And you also have these mixture weights, C sub M. And the update for the C sub M is just going to be the ratio of counts. This is just the same as what we derived before for the discrete case. Remember the C hats and everything? It's the same as that, except these are now no longer necessarily integers. They're kind of real values. So now I've explained kind of how the update works. I'm just going to explain some of the math behind why we do this. And it involves this thing called Jensen's inequality. This is a formal definition of Jensen's inequality, and I'm going to explain what this means, but let me just state the formal definition. It says that for a real concave function phi, for example, a log function, concave means that if you look at it from the bottom, it's kind of, like a concave lens or a convex lens. The point is you should always look from the bottom if you're talking about concave or convex functions. So this is a concave function, this is a convex function. And there's some mathematical definition of what it is, but that's what it is. It says that for a concave function phi, for real non-negative weights ai and real xi, this is always more than or equal to this. Now this is easiest to understand if we notice that let me see. This is basically the same as a kind of weighted sum. It's easiest to understand if we enforce that the sum of ai equals 1, because then this denominator disappears. So in that case, it's the same as saying phi of the sum of ai xi is more than or equal to phi of the sum of ai phi of xi. What this is saying is that if we have a concave function, and we're taking a weighted average of these xi's, if we take the function after doing the sum, it's going to be more than or equal to if we first take the function, then do the sum. And this is only an equality if all of these xi's are the same. Now I'm going to show you on the next slide what this means. This concave function is this line here. And supposing there's just two xi's. Here's one, this is the x value, here's the other. Now, here's phi of x1, here's phi of x2. If we first take the phi and then do the average, we get this value. I guess this assumes that the weightings are approximately equal because the average is kind of in the middle. But if we first take the average and then we take the function, it's more. And this is kind of obvious, why this relates to concavity. In fact, in mathematical terms, this is almost how they define concavity. There's some inequality like this. Anyway, so Jensen's inequality is really a very obvious kind of inequality. And we use this inequality to manipulate the expressions in the log likelihood. Now, the probability of... Oh, this is wrong. I shouldn't have p of theta here. I think what I meant by that is I probably meant something like p of x given theta. And I'm using curly x as a shorthand for the data points x1 to xt. And theta is a kind of shorthand that we sometimes use for all of the model parameters. The c sub s, the mu's, the sigmas. It just means all of the set of those, or, it means everything. Okay, it's equal to the, we're talking about the log likelihood. Oh, you know what? I understand now. This curly p, this isn't a probability at all. This is just, I'm just using this as a name for the log likelihood function. So it's a sum from t equals 1 to t of the log likelihood. And the likelihood is the summation of the individual likelihoods given the individual mixtures. I'm introducing the notation f sub m of theta and t as a shorthand for this because I'm going to have some longer, big expressions that involve that. And I don't want to have to write this all out. So this is the kind of conventional log likelihood. This is what we want to maximize when we train the parameters. So the problem here is that the log is outside the summation. If the log were inside the summation, it would be easy to maximize because everything becomes quadratic. But so now we use Jensen's inequality to push the log inside a summation. This is a little bit of a trick. Now we want to decompose this f function into something with a and something with x. Remember that in Jensen's inequality we have these weights a and these kind of values x. And the a's, you can kind of take them to sum to 1 because it really doesn't matter whether or not they have a scale on them. We're going to decompose this. We want, I don't know if I want to go into all of the details of this. The upshot of this is that supposing our current value of theta is theta bar, we can work out a special function q that's a function of theta and theta bar, such that q is always less than or equal to p, and q of theta bar is equal to p of theta bar. This is
Is that right?
sorry?
Is it always the case
The what?
theta bar is equal to P of theta bar?
Well, sometimes people have an offset, but I guess I'm assuming that I'm defining these without an offset. If we look back at the picture, this, let me see. This inequality somehow relates to this picture, but I forget how. I think I have another picture which shows it more clearly. Yeah, this is the inequality. We think of this as our likelihood function. Suppose our current parameters are at a particular value. We basically derive this q function that's the same as the p at the current value, but is always less than or equal to elsewhere. And this ensures that when we maximize the p, when we increase the p, we always increase, when we increase the q, we always increase the p by at least as much. So there's various manipulations we do using this Jensen's inequality to move this log around. And I think it would be hard to fully explain the details.
Frank has a very good proof in his book.
Really?
Maybe we should.
I'm sure tons of the undergraduates will be interested to read that. This is okay. So let's forget about this proof for now. I think it's a little bit hard to understand in such a short space of time. This is the code for how you would reestimate a mixture of Gaussians. This isn't very complete code because we haven't properly initialized the means and the variances. This is a diagonal case, by the way, assuming the variances are diagonal. So let's see. We just initialized memory for the statistics, for the gammas, the mean statistics, the variance statistics. It's an iterative process, so let's suppose there's 10 iterations. Because each time you only kind of increase the likelihood, you don't jump to the maximum. So you have to do it multiple times. So each time you kind of compute the log likelihoods of each of the point given each of the Gaussians. You compute these ratios gamma between 0 and 1. These are the gamma values that are between 0 and 1. They're kind of like the importance weights on the points for each of the Gaussians. You kind of add up your statistics weighted by the importance weights, the posteriors. And then this is like the update. So this is the discrete update. You just would C sub m is going to be the count for m divided by the total count. That's trivial. Yeah.
D is the total count or the number? It's a number sum.
Well, it's the same, right? Now my plan was to go through a lot of different speech estimation things. I had the problem is it rapidly gets more complicated, and I think I feel a
I think we've probably already gone beyond the point where most people are understanding, at least from the undergraduate side. So I'm a little bit hesitant to go beyond here because here be dragons, you know what I mean? But let me just summarize what the rest of the talk was about. It's basically about various things that have to do with like rotation and scaling of the vector space, because we often use kind of diagonal Gaussians to model our data. And if you think about multidimensional data, suppose it's in 2 dimensions and we draw the data. You sometimes have correlations, like these values are correlated. And our diagonal Gaussians are not really able to model that because if you write lines of equal likelihood, diagonal Gaussians can only give you circles and kind of ellipses that are parallel to the axes. They're not really able to model these kinds of correlations. And you can do it with full covariances, but it's often too many parameters to estimate because you have these whole matrices and it's just too many values to estimate. So in speech, there's a lot of things we do to try to make things more diagonal. So basically, we have these kind of matrix rotations of the speech vectors. So suppose our vector is x. We use transformations like x goes to mx plus a. So this is what we call an affine transform. Affine just means it's just what is this transform called without the a? Is there a name for that?
Linear.
A linear transform. I mean, isn't this linear too? Isn't an affine transform linear too?
Affine has an extra term.
Okay. So basically in speech, there's a lot of stuff to do with like estimating these kinds of parameters. And sometimes there's... we use these for 2 different reasons. One is the kind of diagonalization. Because if you could imagine taking this space and rotating it, it would be more nicely diagonal and easier to model. So that's one of the reasons we use these kinds of rotations. The other is that speakers vary from each other, right? But we don't normally have enough data from an individual speaker to build a whole model of all of speech. So what we do, we tend to use these kinds of affine transforms to summarize the ways in which speakers differ. So what we do is we build a shared model that involves all of speakers, but then for individual speakers we work out, this matrix and this vector that says how do we rotate this speaker to make him or her sound more like other speakers. And the estimation of these kinds of parameters, it's quite interesting if you're into that kind of stuff. So sometimes it's just basically, sometimes it just turns into a kind of quadratic problem where you're trying to you're basically trying to maximize a quadratic function. Like in the scalar case, a quadratic function is obviously, like ax squared plus bx plus c. It's a function like that. And to find the maximum of that is actually very trivial because we just do like d by dx of that. I shouldn't have deltas here, I should have d's. D by dx of that, it's just going to be like, 2a plus b. And this is a very simple thing to find the answer of. Because the answer is like, so 2a plus b equals 0. So the answer is just, b equals minus 2a or something. Now, some of these kinds of estimation problems, they devolve to something like that. This is a scalar case. For the matrix case, it's basically going to turn into a matrix inversion problem. And you can just, we don't really code that kind of stuff. We just call some linear algebra package. Okay, now that's one case. Sometimes it turns into that, but sometimes there's determinants involved too. Like sometimes if you work out your objective function, it's going to have, determinant of m somewhere in that objective function. And in that case, it's not quite so trivial to optimize because the determinant function of a matrix is this nasty nonlinear function. So basically, people have come up with these very clever these very clever algorithms that you can optimize each row of the matrix M in turn, and you can kind of, you know, basically there's some complicated expression for how the determinant varies in terms of a row, and you can do a bunch of math, and it turns out you like have to solve a quadratic equation on each row, and then you can work it out. But it's all the kind of stuff that, unless you're very familiar with these kinds of manipulations and vector matrix calculus, it's going to be hard to follow the details of it. So I think it's best that I don't go into the details. Yeah, so my plan was that there's 2 lectures, right? There's going to be one after lunch. So my plan was to go through all of these derivations, and then after lunch to introduce some of the stuff that we're going to be doing in the workshop, and probably, sorry, not after lunch, after the break, and probably during the break I'll talk with people and try to reevaluate what is more valuable, to go through some of these other standard speech things or to talk about the stuff we'll be doing in the workshop. Probably we should at least talk about the stuff that the speech team plans to do in the workshop, because some people are expecting that. But for the undergraduates who are going to be leaving, it probably won't be very interesting at all, because it's basically going to be more of the same. Like, you know, all of these kinds of things. It relates to all kinds of technical details about, you know, rotations and subspaces and stuff like that. And unless you're already very familiar with speech, it probably is going to mean very little to you. But so let's see how things go. How long do we have before the break? Is it break time? Sorry? The break is now. Okay, let's go. Someone should have told me, because I don't have a watch. So wait, when you say now, you mean like now, or we?
It's 10:30 and we start at 10:40 again.
So yeah, 10 minutes into break.
Okay. Well, let's extend the break then, and just because I think people are getting very tired. I don't think I'm going to be very tired. Let's just have the normal length of break and start a little bit late. Yeah.